Hey there, it's your old pal Keith from wavetables.lol. That's wavetables.lol, home of KRC Mathways, my gigantic collection of single cycle waveforms, wavetables, and even some samples for all sorts of modern synthesizers, like our friend Korg Modwave. And today I wanted to talk about the basic synthesis waveforms, which I have touched upon in previous videos, like the one where I was showing the shark fin waveforms and stuff like that. But I didn't talk about them in the way I'm going to talk about them today. So I wanted to, sort of explain the differences between the various basic synthesis waveforms that we know from subtractive analog synthesis, and see what we can learn about them, and kind of motivate your intuition about the look of a waveform versus its sound, which I think is kind of an interesting topic. So anyway, let's kind of jump into it. Quit being so talky, Keith. Talky. So there are essentially four basic synthesis waveforms, right? We've got the sine wave, and I've just picked this out from the Korg's own basic wavetable, right? So we've got a sine wave in here. The sine wave only has a single harmonic, right? It has the fundamental frequency. It's a single frequency. And, we can, right? We can hear that. That's what a single frequency sounds like. And then we've got the triangle wave, which is related to the square wave. Here's a square wave with a 50% duty cycle. All right. So the triangle wave and the square wave share something in common. They both have only odd harmonics. And so they have that kind of hollow, reedy sound that reminds us of woodwind instruments, right? Now, the difference between the square wave and the triangle wave is two things. We'll get to the second one a little later. The first thing is that, of course, they only have odd harmonics. So the square wave and the triangle wave are similar, right? In that they only have odd harmonics. The odd harmonics in the square wave drop off with an amplitude ratio of 1/n. So, for example, it has a full amplitude sine wave at the fundamental. It has 0 amplitude at the second harmonic, and at the third harmonic, it has 1/3 the amplitude sine wave. And this keeps going infinitely out to infinity. It results in this wave shape. Now, the triangle wave falls off differently. Instead of the odd harmonics falling off with a 1/n ratio, they fall off with a 1/n squared ratio. Okay, and so that leads to this kind of duller timbre. And as I've said before, it's not my favorite of the waveforms, but it is useful, right? I mean, as a modulator, it's great. Maybe not so much as a sound source. And then finally, we have the Sawtooth wave. And the Sawtooth wave contains all harmonics, again, with the harmonics falling off with an amplitude of 1/n. So it's got like a full amplitude sine wave. It's got a 1/2, a half amplitude sine wave at the second harmonic, one that's a third in amplitude at the third harmonic, right? A quarter of the amplitude at the fourth harmonic, etc., out to infinity. And so knowing these kind of relationships, it made me think, well, what's the sound of all harmonics that drop off with a 1/n squared, right? Like the triangle wave. The triangle wave, the harmonics drop off with a 1/n squared relationship. But like, why isn't there a synthesis wave that is all harmonics, like as are found in the Sawtooth wave. Like, why isn't there a 1 over n squared Sawtooth type wave, right? Like, what is that guy? So, that led me to create some wavetables with some very simple code, right? Which is how I do a lot of my waveforms and wavetables, like particularly in the original KRC Mathwaves collection. A lot of the waveforms were created using these kind of spectral techniques. And so that maybe brings us to our next idea we want to explore here is, how is it actually that just summing sine waves could create these sort of waveforms? And is it really true that the waveform is actually made up of just sine waves? We know from the French mathematician Fourier that any sound actually can be decomposed into a series of these harmonics, these what is sometimes called the Fourier series of sine waves that make up the signal. And so one thing I see people asking on the internet with some regularity is, how is it that the square wave is, it takes on the shape that it does? And so let me show you the plots in this wavetable. Let's see, which one is it? Here it is. So here are the waveforms that make up the wavetable that we're now hearing. So you can see in frame 1, there's just a single sine wave, right? We hear that as we hold the note, we get down to that. And then frame 2, this is with the addition of the third harmonic, and you can see it's already starting to take on that square wave shape. And then here's the third frame, is the next odd harmonic being added, fourth frame, fifth, sixth, and you can see, like, by the time we get to like 16, we've essentially got our square wave. And of course we can keep adding harmonics, but we don't really need to add that many to get to what is essentially a true sounding square wave. And these actually kind of have an interesting sound to them all in themselves, because we sort of, we hear that kind of low pass filtering effect in a way with, there's a little bit of interesting resonance that happens. It's as if we, just radically filtered this with a low pass filter, right? Of some sort. It's not, what are you trying to set up? What, huh? I'm not trying to set up anything. I don't know why is that running? Okay. We also did the same thing for the saw. Let's look at the plots for that. That's over here, I believe. So see, frame 1, we've got just the first harmonic, the fundamental, right? And then we're adding another sine wave at frame 2. That's the second harmonic, the third, the fourth, the fifth. And you see it very quickly. Again, we get to the thing that looks like the Sawtooth wave. And, it has that sound, right? Now you can compute waveforms like this in this fashion up to any arbitrary number of harmonics. You could, if you're not convinced that this is close enough to the quote-unquote true Sawtooth wave, for example, you could go out to thousands of harmonics. And in fact, I did that in some other wavetables. What am I trying to say? Let's go and look at one of these. So now that we've motivated the whole idea, right, that the waveforms are, composed of sine waves, and we can compute them in that manner if we want to. Let's go and look at my experiment in changing n, right? So let's look at another plot. So here's a plot that you see when we get to this exponent of 1, we've got the Sawtooth wave. What I did in this particular wavetable, or I did over the course of several wavetables, was change n, right? So the harmonic fall off of 1 over n, make it smaller, and then also make it bigger. So you can see what happens as we change n smaller. We start to get this very pointy wave that has like a kind of a lot of zeros. It eventually gets to this. And these waveforms that have these very, very narrow peaks, they actually don't make anything that's audible and musically useful. So when I did the actual wavetables that I'm going to show you, I just went down to an exponent of 0.5-ish or so. So let's go get one of those. Let's see, they're in KRC Core. Whoops, get rid of that one. Here is, let's see, let's do the exponential square. So here oh no, I wanted the exponential saw, sorry. We're talking about sawtooth waves here, Keith. So you see that in this wavetable, at the 50% position, we've got the true sawtooth wave. And then as n decreases, we get these waveforms. They sound very nasal, right? They're kind of like a nasally saw. And you can sort of see that it's almost as if the sawtooth wave is getting squeezed a bit. And we've seen waveforms like this before, right? Like in the split wavetables that are in KRC math waves. They kind of come out to waveforms that are a little bit like this. And then as n increases, so this is n equals 1, and then it's going out to n equals 4, you can see that the waveform very quickly kind of asymptotically approaches a sine wave. And if this number gets super, super high, you would eventually get a sine wave as that second harmonic just completely drops out. So, this is the answer to, well, what's that? What's the waveform that has all harmonics where they fall off at a 1 over n squared relationship? That's kind of out here. So it just sounds like a filtered sawtooth wave. And, we could sweep this to hear what it sounds like. Let's go from, the higher frequency to the lower. So, that's maybe kind of a useful wavetable itself. It's sort of an interesting sound. I mean, this could be interesting for plucks or something, but that answers that question. And we can do the same thing with the square wave. So when we do this experiment with the square wave, I'll show the plots somewhere. I've got a plot here that shows that. This is what happens. So you'll see that around, let's see, where's 1.0? So you'll see it right around 1.0. We've got something that is like, here the exponent is 102. But it's basically the square wave. As we decrease that exponent, we're getting these kind of, I don't know, they almost look like some sort of like modern architecture kind of thing. But you get these kind of points, these pointy points. And so those sound like this. Now they only have, again, odd harmonics, so they do have that character of the square wave, but they don't have its richness, right? So there we're transitioning from these pointy things where the harmonics are falling off in a slower way, down to the square wave. And so swept in full, it sounds like this. So that's it's kind of interesting. Now you might expect that since we're doing this, we're changing that exponent, right? Shouldn't somewhere in here there be the triangle wave? Because the triangle wave, right, is all the odd harmonics, but they fall off in a 1 over n squared relationship. But we don't find it here, right? So this is kind of interesting. Let's look at this patch. So here I have loaded a different version of that wavetable. So in this one, I've centered it so that the middle point is the waveform that's all odd harmonics that fall off with a 1 over n squared relationship. And then, it does the trick if it goes goes to a lower exponent and then a higher exponent. But of course, this is not, this isn't the triangle wave. But if we listen to it, and I need to turn one of these channels down. Here's what it sounds like on its own. And then over in oscillator 2, I've got Korg's basic wavetable. See, there's the triangle wave. Certainly doesn't look like that. But maybe go up an octave or two. That's the triangle wave. And this is this wave, whatever we want to call it. And you can hear that it sounds the same, right? So what's different about this wave from the triangle wave? Well, it turns out that there's one extra trick to the triangle wave. So the triangle wave is, in fact, all odd harmonics, and they do fall off with the 1/n² relationship, but every other harmonic is rotated 180 degrees. And if you do that, then you'll get the triangle wave. So one other thing I wanted to point out about this is that you might be able to hear that these are different if we layer them. So you see that with this phase relationship, where they're both with the same phase, you get this, it's kind of a pleasant sound. And we can change the way certain frequencies are canceling, right, by changing the phase of one of the waveforms. And this can be kind of a pleasant effect in itself. Like we could modulate that with an LFO. It's kind of interesting. So let's just go, let's turn that off, and let's load up. Here is a wavetable created correctly. So this is all the odd harmonics going from 1/0.5 to, I guess this says 16. Maybe it does really go to 16. I guess it probably does. I didn't really mean to go that far with it. But here you go. You can see that the triangle wave is centered in this wavetable. And so now we've got, kind of a different set of waveforms to see. And you'll see that with the triangle wave formula, what happens is we get these little pointy peaks as this goes lower. And then, of course, once again, as the exponent increases, we get, something that goes toward a sine wave. And so swept, it sounds like this. Okay. So there's a way to get to triangles. And so you can hear, now here's, let's change this. We don't want to sweep it. So let's just, listen to the triangle stacked on top. Two triangles going to the mixer, right? So it's kind of two triangles stacked on top of each other. It sounds like this. Not totally different from that other waveform being added. But we don't get quite the animation that we would get if we used that different one. The changing the phase doesn't do as much here, I think. So that was kind of an interesting and fun discovery. That leads us to another idea. So in the same way that the triangle wave has this, every other of its odd harmonics is rotated by 180 degrees. I was like, well, what happens if we take the Sawtooth wave and do a similar thing? So, how we computed, right? We computed the Sawtooth wave with different exponents, right? What would happen if we rotated every other harmonic, so it would be like we're rotating all the even harmonics by 180 degrees? Like, what waveform does that make? And I will show you that waveform. Let's see. I put it in this patch, and I'm just going to turn down channel 1. So here you can see I've got that same style of wavetable. It's centered on the Sawtooth wave. And I do have some tuning going on. Let's turn that off. Okay, so there's our Sawtooth wave. Now, okay, how is this different? It sounds like Sawtooth wave, right? I mean, it seems like it's almost the same wavetable, but how is it different? Well, it's different in the phase. So here, let's turn up oscillator 1. So here we've got the phase starts at the very top, right? And so it ramps down and then comes back to the top in this version. In this version, if we rotate it 180 degrees, we can see what's going on here. This one is ramping up, okay? And also, as I said, it's the whole thing is phase rotated 180 degrees, but it's also inverted, right, with respect to the first one. So the first one is a downward going saw, and the second one is an upward going saw, which some people call a ramp. So I've labeled this wavetable as a ramp. Now, because these things are just inverses of each other, if we turn them both up at the same time to the same volume and they're aligned with this kind of phase, we won't hear anything, right? They'll just disappear because they're completely opposites of each other. Now, another thing you'll find, so let's change this guy's phase back to 100, well, it's default 0. When we stack them this way, and they're aligned, I guess it's 90 degrees to each other. Well, no, it's 180 degrees to each other. When they're aligned like this, what does that sound like? Well, that sounds an awful lot like the square wave, doesn't it? We can hear that there are, there's maybe only even harmonics in this resulting sound. So that's a very interesting effect. And this reminded me of a really cool synth trick. And I've mentioned this before, but I didn't perform it because I don't think I had a ramp lying around. So I have a ramp here, and so I've got an upward going saw, I've got a downward going saw, and now we can actually construct pulse width modulation. And so you can do this in any sampler or synth where you've got an upward going saw and a downward going saw. What you do is you just put them in the same patch, right? Send them to the mixer. And then if you change the tuning on one of them, listen to what happens. So for very slight detunes, that becomes, it's not like a square wave now. That's square wave kind of sound. It sounds like the pulse wave in a way. And it sounds like pulse width modulation. And in fact, this is pulse width modulation. The resulting waveform here is like when we modulate the width of a square wave. Let's just compare this to doing it another way. We'll look at, I've got some wavetables, of course, that do pulse width modulation. And so here's a patch. Let's turn our cutoff way up. So there's that sound, right? And Gordon Reed, I mentioned this the first time that I talked about this effect. Gordon Reed from Sound on Sound Synth Secrets series wrote a really cool article about this and what happens. And he actually shows kind of an experimental way, but it's sort of mathematically, why modulating the pulse width of the square wave actually does create two waveforms. These waveforms are Sawtooth waveforms, and they are detuned with respect to each other. But there's one more thing that's going on. So what we want to do is we want to modulate this slight tuning offset using a square LFO. So our pitch LFO here is set to a square wave, and now when I play this, it's that you've got that that classic sound where the pulse width is changing. And so you see I'm going to turn this modulator off. You'll see that when one waveform is higher in pitch than the other one, you get this barber pole effect that's going one direction, and then you hear it going the other direction when the pitch is negative. And so that's why you modulate this with a square wave type of LFO. And if you go really big, of course, you start to hear the tuning. But if it's very small, you get the PWM effect. And you could exaggerate this by further moving the pitches with respect to each other and kind of get different effects. Or you could use different wave shapes for the LFO. Let's see, is this actually happening? Yeah. Change their speed for different effects. So that's really interesting to me. And that's kind of wacky. Kind of wacky to have that intensity way up like that. It should just be small. But that's really cool. It's a fun thing to know and share. And I think that's all I wanted to talk about today. So there's a little fun synth tip for making, I mean, come on, PWM sounding stuff just sounds huge, and it's fun to filter. Toot, 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 toot. I'm sure I'm making filter face. Wow. Right. That's it. Have fun. Go get KRC Mathways. Like and subscribe if you like talky synthesizer content like this. Have fun. I will add these wavetables to KRC Mathwaves sometime soon, but I might play around a few more little ideas around this. And then I got to do all the stuff like, convert them to all 4 of the formats and stuff like that. They only exist in my ModWave right now. Anyway, have fun. Talk to you later. Bye.